Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Joyce Guzik with us today. Hello, Joyce.
Hello. Nice to see you.
Well, it's very nice to see you here on this May 16th, 2023, as we record this. And that background is pretty awesome. Where is that?
Well, this is White Rock Overlook Park, which is only about a mile or two from my house in Los Alamos County, New Mexico. And this photo was not taken by me. It was the astronomy photo of the day in April of 2020, right after the pandemic started. I thought it was cool to have a picture right near where I live. That's the Rio Grande River in that picture. And I have to tell you, you might see strange reflections above me because my chandelier is just above my head and it kind of comes in and out of the field of view. So
it gives you a nice, well, it's either a funny hat or it's some alien object coming down in Mexico there. So it's all good.
Like a funny hat. It's right over my head.
Very cool. Very cool. And Joyce, what do you like to do for research?
Well, when I started my career, I was doing a lot of helioseismology, solar oscillations, and I still do some helioseismology. But I've also worked on several other kinds of variable stars, and you'll hear about some of them today, the Delta Scuti and Gamma Doradus, main sequence pulsating variable stars. Cool. And I've also worked on Cepheids recently. So nice. All over the HR diagram, I love looking at variable stars and comparing and contrasting what they're doing and what their physics is.
Very cool. Very cool. And that is going to bring us to this very awesome AJ article. It's open access, people. We go grab a copy for free. We're in the open access area. And variable blue straggler stars in the open cluster NGC 6819 observed in the Kepler Superstamp field. And Joyce, take us away.
Okay, thank you. I hope this will be interesting for you. So I didn't really choose this topic myself. My second author, Andy Barron here, is an expert in SDB, subdwarf B stars. And he and his students had been looking at stars in this superstamp field that was observed by Kepler for 4 years, almost continuously, except for a couple of times when the cluster fell on a dead CCD array. And so they discovered many kinds of variable stars in the superstamp field. So Andy and his students went and worked on the SDB stars, but he needed someone to look at the Delta Scuti and Gamma Dor stars. So he had contacted me, and I had done an article for him, a review article on Delta Scuti stars, and that's why he knew who I was. So he asked me to collaborate, and so I agreed. And then I recruited a couple of other friends, Ann Hedlund and Jason Jackowitz at New Mexico State, and who had been working with me on Delta Scuti stars, and Lori Dahlsberg, who was a late addition to the paper, and she is not an astrophysicist. She's a data scientist.
Cool.
She has a degree in economics. So she was, when I was trying to do the revisions for the paper to answer the referee, she said one day at lunch, "I'm really bored. Do you have some data I can work on?" And I said, "Oh, I have lots of data you can work on." Awesome. And so I had her analyze the data, and some of the plots you'll see are from some of Lori's ideas.
Very cool. Very
cool. It was great. Okay, so why do I even care about this cluster? Well, it was in the Kepler field, and it has this very unique data set of one data point from the Kepler spacecraft every 30 minutes for almost 4 years continuously. So it will be very high precision, very accurate data. And of course, if you can get data like this and discover pulsations in stars, then you can start doing astroseismic analysis and figure out more about the interiors of the stars and other things like their ages and masses and things like this. So it's always hard if you get a star just sitting out in the field, unattached to anything. What is its real age, for example? But for this cluster, we have an age from the cluster turnoff that is very well known, around 2.4 billion years, or about half the age of the sun.
Okay.
What's more is there are a lot of blue straggler stars that were discovered in this cluster. Okay. And these are stars that are off, they're above the cluster turnoff on the main sequence, and you'll see some of those in a later plot. They should have left the main sequence and have become red giants, but they haven't. And this has been a mystery for ever since I've been in astronomy. What is the origin of blue stragglers? Are they the result of a binary merger? Are they, which is what a lot of people think, or of mass transfer from a previous star that formed a common envelope and created mass onto it? Are they was there some extra internal mixing from a lot of convective overshoot that kept mixing material into the core? So there's been a lot of ideas over the years. So by having pulsations in blue stragglers in a cluster with a known age, we've got a lot of constraints, and we can perhaps shed some light on the origin of the blue stragglers. That was kind of our motivation for this paper. So, so Andy took the data, and let's go down a little more to the pictures. We can take a look at this. So this picture on the left shows the Kepler field of view, and you see those 21 CCD arrays that were pointing at a particular field of view for the 4 years continuously. And then you see the NGC 6819 cluster is right down there in that CCD, which if depending on how the CCDs are oriented, because they move them, I think they shifted them every once in a while. It would sometimes it fell on one that had broken during the mission, but most of the time it was on a set of CCDs that you could look at continuously. And then on the left side, you see what the Superstamp is. 200 by 200 pixel field of view centered on that cluster. So probably the first thing you have to do, if you find, you can look at every one of those stars, every one of those pixels, look for variability, figure out if it's in the right frequencies to be pulsations, which is what we're going to do here. And then, but then you have to figure out, is that star actually a member of the cluster? It could be a background star, it could be a foreground star, right? So Andy's student Sachu did some of that work, and they used what did they use? Proper motions and parallaxes. And the cluster members should have about the same distance and should be moving in the same direction. So using those two things, they were able to determine with 99% probability that the 5 stars in this paper were cluster members. Then we can go on from there. Okay, so we can go further down. This picture is not mine. I reproduced it with permission from Konstantin Delianis, and he did a really nice job of making a color magnitude diagram of this cluster and fitting isochrones to it, so you can see the different ages. So around 2.4 is a good average for the age of this cluster. Although, did you have a question? And then I put a circle over there around some stars that are, they may not be the stars in my paper, but they're blue stragglers. They're stars that are bluer than the rest of the cluster turnoff, and they should have left the main sequence and been off to the red there, but they're sitting over there, and we have to figure out what they are.
What they are and why.
And why are they over there, right?
Very cool.
So, and I like this one too, because Konstantin corrected this this figure for interstellar reddening, and this cluster is really far away. It's, I think, 2,000 something parsecs, 6,000 light years. So interstellar reddening is really important in getting the absolute magnitudes of these stars.
Very cool.
Okay, so we can go further in the paper.
Very nice, John.
Scroll down. So this is just cluster membership, as I said, around 98-99%. And there you can see the distances of the 5 stars that we looked at. They're all around 22,000, 2,600 parsecs. So pretty distant. These are fairly faint stars, unfortunately, for us. So
at that distance, very good.
Okay, so let's scroll down some more. Then I talk about individual stars and how we did some of the actually how Andy did some of the light curve analysis. But this first one will show you one of our stars. This is which is the first one, KIC 5024468. So this is a It turns out it's a Delta Scuti star. So on the left, you can see a zoom in of about only 5 days of the light curve. And the points are the blue dots. So
Nice.
1 point every 30 minutes. So you see it going up and down, and there are many frequencies beating against each other constructively and destructively to make this interesting pattern. To do a Fourier analysis of it on panel B, you see that there are a lot of nodes right at 12 cycles per day. So this is about 2 hours, period, 2 hours. That's exactly what Delta Scuti stars are supposed to show. Cool. Period of their pressure mode pulsators, period about 2 hours. So then you can pre-whiten these modes. You can start subtracting the highest amplitude modes out successively. Okay. And get fainter and well, you can get to lower and lower amplitudes. And I think on the right, I've zoomed in on some of the lower amplitude modes before the pre-whitening. So there actually are modes that are all the way down at 4 cycles per day or 1 cycle per day. And those modes probably aren't Delta Scuti pressure modes. They're probably gamma Doradus gravity mode pulsations. And what we found from Kepler, a big surprise, was that many stars, maybe most of the stars that in the Delta Scuti and gamma Dor pulsation instability strips are hybrid pulsators. They pulsate in both types simultaneously. And theory does not predict this, and theory does not explain it very well. You should get one or the other. And we're getting a lot. And, you know, if they were right on the borderline, yeah, maybe you could get maybe. But here we're getting both kinds of modes. So this one was predominantly Delta Scuti modes. And after Andy quit pre-whitening this star, he had 236 separate pulsation modes. Wow. So that's the record for this particular set of 5 stars. Our second highest was 124 modes. Very cool. This is an example of what the Delta Scuti, but also some gamma Dor modes looks like. So let's go down further in the paper and let me see if I can find a gamma Dor example. Okay.
2448 looks like we're gonna have some gamma.
There's hybrids.
502.
That one's pretty good. 5024455. Yeah, that'd be good. So here's an eclipsing binary that was contaminating one of the stars.
Drop
so
out.
Then we had to subtract that out, and which we did. So that was, you have to watch out for that. So those stars are so close together. One star very nearby can contaminate the light curve of the next of the star you really want to look at.
Oh, just a question as we go. These are the blue stragglers that we had circled in here?
Yes. Yeah, okay. They're not exact. They may not be those particular blue stragglers. I have not gone back and tried to correlate them.
That's fine, but these are the blue stragglers in the cluster. Yes. Okay, I'm good. I'm good.
They're all blue stragglers, except the last one, which we have time, we'll do it. I could never figure it out. Okay, we're going to do the
so there's our eclipser, and this is our
this is what happens after you've taken out the eclipse. And this may only be the second star. We're going to look at the third one, 502445. Let's take a look.
That one's going to be
yeah, that one is good.
Ooh, yeah. Wow.
You see how, so it has, this is a 20-day zoom in. So you see the periods are quite a bit longer. It's going up and down, but not a 5-day zoom in wouldn't have shown you as much. And then if you look at the Fourier transform of that, you can see on the right there are many modes between 0 and 5 cycles per day. So that's about one cycle per day, 1 to 3 cycles per day. If you flip it over, it'll be days, periods of days. And these are the gamma Dor gravity mode computers. So yeah, so that was our best.
Interesting.
For just pure gamma Dor. The other two that I'm going to skip are hybrids again. That had 124 modes and 53 modes. You can keep scrolling.
Okay.
Let's see.
There's one of
I don't know what that is. We'll look at the next one.
5113.
This is a Delta Scuti primarily.
Definitely.
This is showing an example of a star that has frequencies very close to the Nyquist limit, which is a frequency limit for 30-day cadence evenly spaced data. So if you figure out what that is, that means that you really can only detect things below 25 cycles per day, the Nyquist limit. However, because Kepler was in a trailing orbit around the sun, and we had the light delay time travel to the barycentric center of mass for our solar system,
Mhm.
we had 4 years of data, you could break a degeneracy between frequencies above and below the
Oh,
Nyquist
nice.
limit.
Yeah.
And
Nice.
it turns out that anything that has an amplitude bigger on the above 25 days than below 25 days, that's a real frequency. And
Cool.
anything with the amplitude bigger on the left side, that's the real frequency. So on the
Very
left,
cool.
you see right down the middle of that is the 25 cycles per day. And
Mhm.
so once you picked through here and found all the modes on the right that had
Wow.
a bigger amplitude than the ones on the left, and we could tell those were the true frequency.
Cool.
So, yeah.
Very cool.
So yeah, so that shows an example of the of that effect.
Hmm.
Breaking that degeneracy with the Kepler data set, the 4-year time series. Okay, so this is another weird star. This is my last one. And this one is not, it's
Wow.
kind of right on the main sequence turnoff. It's not a blue straggler. We don't know what it is. We think
Wow.
it could be a contact binary with mass transfer, with
Okay.
one star transferring mass on the other. And that's because it was also showing up in X-ray data as an X-ray variable.
Ooh.
So
Okay.
maybe some matter is accreting onto the other one star and
Mhm.
causing X-ray variability. So it's still a mystery. Doesn't have
Mysteries.
pulsations, so I didn't really want to, interpret it. Although those frequencies are in the right range to be a gamma door or a delta Scuti, but there's really only 2 modes
Yeah.
beating against each other. So
Mhm.
I can't really say anything about it.
I like
Could be,
mysteries. Mysteries are good.
yeah, mysteries are really good. Okay, you can go further down now.
All
Um,
right.
this is the
Go
picture
down.
on the left side that I borrowed also from Gosnell et al. And the star X9 is that mystery star. It's the X-ray
Ooh,
variable.
right.
So she has all the X-ray variables in red on this picture. So,
Okay.
and
Good.
it's not it's not in the blue straggler region, but it's kind of off of the main sequence too. So
Yeah.
I don't know,
Toward the red. A little dimmer too.
right? Okay, and it's too cool to be a delta Scuti or a gamma door. So, it's kind of
But it has
mystery
X-ray.
star, mystery star.
Absolutely.
Okay, so
Neat.
let's go further down.
Okay, and these things are relatively metal poor.
Yes,
Table 3.
yes, but those metallicities really bother me. I was hoping that since they're all these stars are in the same cluster, shouldn't they all have the same metallicity? Since
That's
they
what we
all
tell people.
formed at the same time, but there's a lot of spread
Scatter.
and a lot of uncertainty. And I can't really say I could use the metallicity as a constraint for
Yeah.
these stars because
So
it's,
those are spectroscopic metallicities?
yes, yeah,
Wow. Okay.
this is a low resolution spectroscopic
Okay.
study. And
Hmm.
I've tried looking online for other metallicity
Curious.
values, and they're kind of all over the place. They're kind of around solar, but they're not any closer together
What
than
you
the,
see here. Yeah.
right. So
Okay.
that's kind of discouraging.
Hmm.
I could use
Hmm. The mysteries are adding up here.
that. I know.
Okay. Oh, yeah. Okay. Spectroscopy, of course, you did. Okay. Very good. The blue straggler modeling.
Oh, yes. So the referee on the first time through asked me a question. He said, well, this cluster has some promise to maybe understand the blue stragglers, but modeling blue stragglers, even in clusters, has been, the promise hasn't been realized.
Right.
People haven't actually figured out anything about blue stragglers in clusters from astroseismology. So how could you do that for this paper? And I thought that was kind of beyond the scope because it was AJ, it's more of an observational paper.
Right. Yes.
And also, but what I did in this section, this was the new section for the revised paper.
Mm-hmm.
I went through the literature and I talked about what other people have done with blue stragglers in clusters, and then also pulsating blue stragglers in clusters, and also blue stragglers that weren't pulsating in clusters and how and what kind of modeling has been done. So it's more of a review about what's the state of things. And then finally, I got to a section where I talked about what would you need to do with the MESA code, to the MESA stellar evolution code, to model blue stragglers and then look at their frequencies and then compare. So I did go through an outline of that, maybe a little bit later in the paper, which it's past this part maybe. Let's go forward some.
Okay.
Yeah, this is the outline, where these 5 steps on the left on what you could do with MESA. You could model say you're going to do a binary merger scenario.
Okay, right.
You could model the two stars of lesser mass separately, but there's a lot of free parameters there. What are the masses? How far apart are they?
Yes.
Then you can evolve it through the mass transfer phase and into the common envelope phase, and then the code doesn't go further currently. However, there are some people that have made extensions of the code, both for the MESA summer school, I think is where I pulled some of this from Gottberg et al. 2021.
Yes.
MESA summer school. They have a nice outline and examples of enlists on how they could continue through the common envelope phase, do the merger, strip off the rest of the envelope,
nice.
then continue the evolution. And then you want to continue the evolution till 2.4 billion years, because we know the age, right?
Right.
And then you want to calculate the frequencies and see if they agree at all with what we observed using gyro, for example.
Okay.
So there's a lot of free parameters in that. It would take a lot of trial and error. It might be best to do some kind of a broad sweep grid of binary merger models, and that would be a good project for somebody who had infinite computer time or whatever, machine learning techniques to make
or an AI, right.
And then you could just pick the ones out that match the right age and other properties of the star and see age, mass, whatever, and see how you do. That's kind of what
I'm glad you're laying out a research project here for somebody.
Oh yeah, it's a big research project.
Big one.
I met some people at Northwestern University in April this year who are Vicky Caligera and 3 or 4 of her students and postdocs that were doing different kinds of binary merger modeling. And I thought they would be perfect. They could do this project if I had time. So there may be other people, right? So what can I do? I didn't want to go through that because that's such a
that's not what this paper is about.
Way past what I could do. So I said, well, let's take a look at using astroseismic scaling relations.
Okay.
Right. And for the sun and sun-like stars, we have scaling relations that you can use to figure out, I guess, a mass and a radius, for example, from a temperature and a frequency spacing of the star.
Yes.
So you can do some things like that.
T-modes.
So there are analogous things for delta Scuti stars. They don't completely obey an asymptotic frequency spacing like solar oscillators. They're not perfectly equal, but they're kind of got some, there's some
sort of there.
Right. So people, Suarez et al. And some other people, Garcia Hernandez, both calculationally and observationally made a relationship between mean density and average frequency spacing and calibrated it to binary stars with delta Scuti stars in them. Cool. So they could get a good, then you would know the mass and you would know the radius and from the binary evolution, then you can calibrate this. So they made this relation, and I can use that for the delta Scuti stars, which I did in this paper. There's another relation for temperature, and we can go down further.
That one is
first let's stop on those first. I guess I'll give you those spacings.
Okay.
So you have to figure out what the spacing is, and look at those 4 plots here. Okay. So what we did is we kind of, Lori Dalsberg, who was the data scientist, I had her do this. Well, she found this in the literature, but I had her do the brute force approach of just subtract the frequency of every one of those 214 modes from every other one, right? Every other mode. And then a histogram of how the most common spacing. And so the smallest, most common spacing would be the good delta nu. So this first star looked like around 5, 4.5, and the other one about 5.5, 6 cycles per day. And then Andy likes to use this Kolmogorov test that Steve Kowaler gave him a long time ago from a paper, a Python script to do this. And he found the sort of a probability of the best mean spacing using this software. And you see, they agree pretty well. There's the little bit below 5 is that dip on the left. And a little bit above 5, 5, 6 is the dip on the right. So the dip on the right picture.
Oops, sorry.
Yeah, right there. So there's a lot of other possibilities. And in particular, we got fooled on the left star, but we could figure that out. The star on the left that says it's at 5, there's also another one at about half that spacing, at around 2.4.
Oh,
and that actually is more reasonable. If you use that 5 one, you get a star that's 8 solar masses, and that's way too hot for that delta scoop, way too high. So way too high luminosity, but that one gave you just a great, it agreed with the other data. So, so we use that one. Okay, so let's go on. We'll go down.
Our T effective scaling.
Yeah, this is it's got a little bit big uncertainty, right? But again, with the maximum amplitude frequency. So, you know, there was this like a broad set of frequencies, and there was one that had a maximum amplitude. So if you take the frequency of that maximum amplitude mode and plug it into this equation, you get an effective temperature. And this was calibrated with thousands of delta Scuti stars from the Katrin Uderhoven's paper from Kepler. So it isn't great, but it's something. So we got a temperature, and it gave a reasonable temperature. It wasn't crazy, so it agreed okay with spectra. Yeah, it was good. I didn't hate the temperature. It was okay. All right.
Very good.
So then you go down some more, and I made a spreadsheet that is this the good picture? Yeah, this one's okay. Look at the table.
Yeah, I was gonna say this table is important.
Yeah, right. So here are the 2 delta Scuti stars that had lots of frequencies. The temperature is from the astroseismic scaling relation. The mean density is from the mean density delta nu relation. And then I use those to get, so you have a mean density and you have a temperature. And then if you know either the log G or the luminosity, you can get the mass and radius. So I had estimates for both the log G and the luminosity. And so I just moved them a little bit up and down to make them self-consistent. And then I derived these masses for the stars. And those are reasonable masses for a blue straggler, 2.15 and 1.59, and reasonable radii. So for a main sequence blue straggler. So,
hanging together.
Use the frequencies to come up with a good estimate of the mass.
Global's pretty good. Yeah, very good.
And now I didn't know what to do with the Gamma Dor stars. And those had, you know, hundreds of those G mode frequencies all stuck together. So looking at papers by Van Rieth, Sayo, and Lee, they started to try to analyze these stars, and they had over 2,000 Gamma Dor variables, and they found some sequences of period spacings in about a third of them. And they were able to correlate the slope of those period spacing sequences with the near core rotation rate. And that's comparing some Mesa gyre models and with the data. And even if they find a particular slope in a particular period range, they can even tell you this is a Rossby mode with angular degree 1. This is a G mode spacing with angular degree 2. They can pick some things like that out. So I was looking for those in my stars, and I didn't actually find. I found some possible hypothetical ones, but it wasn't enough for me to really say they were real. Okay, and we can scroll down and look at what I found.
Let's see what we got. Figure 13 and 14.
Yeah. So this is without any extra pre-whitening. I couldn't see any slopes in there at all. You know, you could say, well, maybe there's some points here that lie on a straight line, but want to bet on it.
With a huge scatter.
Oh, you just can fit anything.
Yeah.
And I had Andy go back and try to
Dots.
whiten more in the gamma door frequency range.
Okay.
And on the left, I found a lot of points there in that blue line, but I still don't believe it. And on the right, I found the red and blue line. They look a little more convincing to me, especially because there's like a gap below that blue line at 0.9. There's no other point there, and there's a gap under that other one. So I did not say in the conclusions I found anything. I said we tried, but we didn't find anything.
Right, suggestive maybe, but
so, yeah,
nothing you stand on.
Right, but these slopes would be about the right slope in the right place in the period ranges to identify them as a particular kind of mode if they were real.
Right.
If they were real.
Yeah, it's negative.
I had to leave it at that. So I think that's all of my paper. All of my paper.
Cool. Oh, I do want to mention there's this very awesome appendix.
Oh, yes. So it's one thing to just make a picture of the Fourier analysis, the amplitude spectrum, and you see a bunch of peaks. But for the future, if people want to try to model these stars or see if they can find some patterns in the data, here we've listed all of the frequencies, all the periods, and all the amplitudes and their signal to noise for all the significant modes for 5 stars. So it just goes on and on. I mean, all 5 stars are just listed in order, and it's a machine readable table. So you can download this and play with it yourself, or try to make models that have these kinds of period spacings or these kinds of frequency spacings that would maybe be good matches to the blue stragglers. So.
Yeah, very cool. The other thing I would like to highlight here for those who maybe not be familiar with it, I want you to pay attention to the number of significant figures in those periods. Okay, that is pretty impressive.
Yeah.
So if you want to be looking for effects, there's plenty of room within the data to massage that. So very cool. Very cool. Joyce, I want to thank you so much for walking us through your very lovely article on NGC 6819 and blue stragglers. Very cool.
Thanks for the opportunity.
Sure. And you hinted at it a couple of times as we went through, and so I will maybe push on it a little bit. And so where do you think we go from here over, let's say, the next 2 to 5 years on this topic? Are there additional observations in the pipeline, maybe on specific blue stragglers? Is there something that maybe some of the forthcoming astroseismology missions might be able to do? Plato, for example, is there something in Kepler that could be done? You mentioned a little bit about the modeling. So just sort of generally, where do we go with this over the next couple of years?
There's many directions you can go. These stars are pretty faint. I would like to look at more brighter Delta Scuti stars that maybe we can get more high resolution spectra, get some metallicities. I don't know what's a good cluster to target. A lot of people are targeting the Pleiades right now as being a really promising cluster with Delta Scuti stars in it. For me personally, I am planning, I'd like to find some collaborators to do some of this binary merger grid of models. That would be really cool to try to do that and target these stars. I would like to, Andy found 8 other stars in the field of view that are Delta Scuti Gamma Dor stars, but they're not cluster members. They're not cluster members. But they're still interesting stars, and I'd like to just publish the analysis on them or see if we can learn more about what those stars are exactly. So we're working on that right now. And then the TESS spacecraft has found many thousands of Delta Scuti and blue and Gamma Dor stars. So I'm going to try to model some of those next, I think.
Very cool. Very cool. Nice. Well, I really look forward to seeing this topic, both observationally and theoretically, advance over the next couple of years. It'll be very exciting. Maybe we'll figure out what blue stragglers are.
Well, I hope so. It'd be nice to get more clues about it. And,
or at least constrain it a little bit more than it is right now. So, yeah.
I think there's one thesis project that I mentioned here in my paper where they did some pretty good analysis on a Kepler blue straggler.
Okay.
That they found out quite a bit about it, but I think they decided, I heard the talk that it was a binary, some mass transfer, but they couldn't find the binary companion, right? So is it not visible, or
Right. Or is it not there?
Not there. Right. Yeah. Right. Mhm.
Very cool. Very nice. Thank you so much, Joyce. That was really lovely. It's a nice article.
Thank
And
you.
that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.